Hello everybody, I'm giving you a duplicate presentation on trees. The recording of the session on Friday failed, I'm afraid, so I'll make a substitute video consisting probably of three parts. This is the main part. The other parts consisted in my giving you an overview of the work that I intend to cover with you over the next fortnight. And I covered some of the general basics of Java. In particular, I showed you a document called Objects, and that's actually very important for an understanding of this lesson, on the grounds that I'm going to create nodes of a tree in Java, and you need to understand how to do that. And secondly, I also gave you some comparative details of the main program structures in Java as compared to the ones that we did last term using Python. So anyway, we'll see how we go. Um, so trees, all right, and the intended learning outcomes of this particular session is that you will learn a fair amount about trees and different types of trees, and in particular you'll learn about the structure of trees as they are found in computer science. I'm going to show you how to implement a binary search tree uh, in programming, so I'm going to use Java to implement that. And thirdly, I'm going to show you three main ways of what's called traversing a tree. And what traversing a tree actually means is simply that it's a way of systematically visiting every node of a tree and possibly processing the data contained in each of those nodes. Right, so let me give you an idea of the content. So first of all, a characterization of trees. First of all, a tree is a non-linear data structure where the nodes are connected by a directed edge. In other words, I'm going to represent a tree in two dimensions, graphically in two dimensions, and each node of the tree, it's really is going to contain data, and two nodes might be connected by an arc representing a branch which is directed. I mean, we're typically moving down from a root node all the way to a leaf node. So I can give you a definition of a tree. It consists of a root node and one or more subtrees. And if you think about that little characterization, it's recursive because I'm defining a tree in terms of subtrees. And the tree that I'm talking about is going to be defined in simpler trees, namely subtrees. And eventually, a subtree will consist of just simply a single node which contains data, and that's called a leaf node. So the general properties of a tree are is this. A node is distinguished as the root node, and that's going to be at the top of a tree. And of course, the tree is going to be represented in the opposite way that you'd imagine a tree to be represented. In other words, the tree is actually going to grow downwards from its root via all its branches to the leaves on the tree. So I'll give you a clear diagram in a moment. And every node appearing um, in the tree is that every node, apart from the root, I think, is connected to another node by means of one of these directed edges. And importantly, every node in the tree can be reached via visiting the node. Starting off with the node, you can reach, there's no doubt about it, you can reach every single node, including the leaves, from that by just by following a path using the varied branches of the tree. The edge from a parent to a child. So we can talk about a node having one or more children, and the connections between a parent node and a child node is again directed. It has a sort of direction. So let me show you a diagram. Here we are. We've got a root node here. Notice that the tree is actually growing downwards from the root, and everything in circles is a node, and including the all the nodes that don't themselves have children. These are called leaf nodes. So this parent node has actually got 3 children. This node has exactly 1 child, and this node has got two children. So there's no problem in understanding what a tree is so far, but as I've said already, a tree is definable by means of using a recursive definition, a definition that involves the term to be defined itself. So a set of nodes and edges comprised of a parent node and all of its descendants is called a subtree. Okay, so let me give you an example. Here's a set of nodes, D, E and F. So there's a parent node, and I'm looking at all its descendants, and it's only 2, E and F. This node doesn't have any children, so the subtree is actually C on its own. B, if you think about B with its child G, B is a perfectly good subtree of the whole tree, in the sense that here's a node and here's its descendant. There's only one. So a subtree might actually consist of just a leaf node on its own. Here is a perfectly good tree, and it's technically, I mean, if I were to look at it, it's a leaf node, and therefore it's a subtree. But if you really looked at E in isolation, it's probably like a root node. I mean, if I've just got E and nothing else, E could be taken to be a potential root node having children. So a tree is similar to what's called a graph in mathematics, and in trees the connection is directed from a parent to its child nodes only. So the only given a particular node, the only connection it has with other nodes is a connection perhaps coming from its parent or its connections with its 0 or more children. All right, so that you could have a node on its own, no children. Well, that's fine. That's a sort of degenerate case of a connection existing. It's no connection existing. Or it could have one child, and the link between the parent and the child is a directed link. Or it might have 2 children, or 3 children, or n children, and the connections between the parents and the children are all of the same kind. They're directed connections, a connection having a particular direction. So the key property that distinguishes a tree from a graph is that a graph can consist of cycles. It can have cycles in it. In other words, two child nodes might be connected to each other. And let me explain what I'm talking about. Have I got a graph? No, I haven't actually got an indication of here. And perhaps I can, hopefully, if I can find my magic pen and my hitherto untested electronic writing board. I mean, I could have a. Let me see if I got. No, I haven't got access to. I haven't got any sort of access. So I'll return to this a bit later on. Or maybe. Let me see if I can do this. No, I can't even do that. I can't use my camera. I'll give you an illustration of what a tree having cycles looks like, and it just means that if you have a node here and two more nodes here, the child might actually have a link back to its parents. And that's a cycle. That's a cycle, and it makes life in other contexts quite tricky, because if you want to find a route from here in London to this seaside resort called Skegness, you've got to be very careful of not. And you're constructing a route finder. What you don't want to come up with is a graph indicating a route from London to Skegness in particular, but it shouldn't have any cycles, because you don't want to go back to Lincoln on the way to Skegness if you've already been through Lincoln, or you don't want to suddenly find yourself in a place called Laos and finding yourself going back to Lincoln before going on to Kesteven in Lincolnshire. So you don't want routes. If you're thinking about finding a shortest route, you certainly do not want to include cycles in that route. So anyway, I'm not quite sure where I am here. So what I'm looking at now is the construction of, I think I've got here, yeah. So what I'm looking at now is the idea of a binary tree, and the characteristics of a binary tree. Very simple. Each node contains a particular data value, some data, and the value in a left child node is less than the value in a parent node, and the value in a right child node is greater than the value in the parent node. And duplicate node values are not permitted. In other words, if you've got a value, say 10, within a particular binary tree, the 10 is not going to occur in more than one node. All right. So let me demonstrate all this. Right. So how do you construct a binary tree? And let's see a binary tree in an operational context. So let's construct a binary search tree, what's called a search tree, from a sequence, so that the sequence is going to become ordered, and thus the elements within the tree can be searched for very efficiently and very quickly. So in other words, let's consider an arbitrary sequence, 11, 7, 8, 25, 15, and so on. And I'm going to build a binary search tree step by step. So I'm going to look at the first element of this sequence, and I'm going to make that the root of the tree. So the first element of the sequence is going to be the first element that I include in the binary search tree. And the next element, namely 7, in the sequence is placed, well, where? Where am I going to put that? I'm going to place it, because it's less than 11, I'm going to place it as a left child, because it's less than the value of the root. If it wasn't, if the second element was 99, I'd actually place it to the right of the root node. So here we go. Given the sequence 11, 7, 8, 25, 15, 28, I'm going to start with the root node and I'm going to add 7. Well, I've got to perform the test. Is 7 less than, equal to, or greater than 11? Well, it's less than. So I'm going to create a child node and put 7 in that node. And I'm going to take the third element and starting at the root, I'm saying is 11 equal to, less than, or greater than 11? Well, it's less than. So I'm going to put it somewhere on the left, and then I come across this node, which I've just added to the tree, and I do the same test. Is 8 less than, equal to, or greater than 7? Well, it's actually greater than 7. So I'm going to construct a new node and insert the value 8 into that node. And just one more time, looking at the number 25, starting at the root node, is 25 less than, equal to, or greater than 11? Well, it's certainly greater than, so I'm going to construct a node and put 25 in it. Okay, and I carry on in a similar fashion, and that's I'm giving you, well, what I've given you is a little algorithm, a little rule for constructing a binary search tree from a given sequence of elements. But the one thing I want you to notice is that I could build a binary search tree for characters of the alphabet, for all the Roman alphabet or the Greek alphabet, because ordinarily the letter A is thought to be less than B, B's less than C, C's less than D, and so on throughout the alphabet. So I could represent the string Christopher, for example, by means of a binary tree very easily. So let's just sort of move on. So I've constructed this binary tree. 11 is the root, and here's the algorithm. Well, here's the working of the algorithm. So check all this out, make sure you agree with it, because somebody might have made a mistake in the construction of this tree. And so okay, so so and so on. So I've actually worked through the whole tree for you there. So let's have a look at the issue of searching for a particular value in a given search tree. For example, does the number 15 occur in the search tree? Well, what's the method for performing a search for 15 in the tree? I'll tell you. Oh, it's very similar to the rules for constructing a binary search tree. You start at the root node, and you compare, I can't remember what we're looking for now, I think it was 15, and you ask yourself the question, is 15 less than, equal to, or greater than 11? Well, it's greater than. So what I do is to follow the right child, the subtree lying and starting with the right child, if it exists, that is. and I perform exactly the same test. Is 15 less than 25, equal to 25, or greater than? Well, it's actually obviously less than 25. So I go down this directed arc, this directed link, and guess what? I find 15. So just stand back from this a little bit and ask yourself what's actually happening. Is that uh, it's this. When I start the search, I'm actually looking in either the left-hand subtree or the right-hand subtree. Well, the example I've just chosen, I'm looking for 15. I'm completely ignoring the left-hand subtree and focusing. Whoops! What am focusing? Where am I? And focusing on the right-hand subtree. And in 2 steps, I found what I'm looking for. And of course, 15 might not have existed, and it wouldn't have existed if this was actually the number 16, because I'd search here, is 15 equal to or less than 16? Well, it's less than. And the only node I've got here is the node containing the value 20. 12 doesn't have any subtrees attached to it. So I'd have to report the fact that the binary search tree does not contain the value value 16, I think it was. No, 15, sorry. Because I assumed that 15 had been changed to 16, and I'm looking for 15. So again, this gives you an illustration of the method of searching a tree for a particular value. So the example is I'm looking for a 3, and of course I'd take a left hand and a left hand, and golly gosh, I find 3 here. If this node didn't contain 3, but it contained 2, I'd have to conclude that the subtree does not contain the value 3. Right. So what I've just invited you to reflect on is the fact that at every stage in applying the rules for search, I'm splitting up the tree into 2 parts, the left part and the right part. Imagine that the binary search tree consisted of 2 million nodes, and each node contained mobile phone numbers. There's a huge number. There's a huge number of EE phone numbers. I've no idea what the exact number is, but it's certainly in the million, probably in the millions anyway. So, supposing I'm looking for the number 07576735086. Well, what I can do is to first of all compare it with the mobile number stored here. And it turns out, perhaps, let's assume, that it's greater than the mobile phone number held in the root node. So I'm going to follow this path here and then perform the test again. Notice what's happened. I'm completely ignoring the whole of this possibly enormous subtree which might contain 1,000,000 numbers. I don't have to search through those. In fact, I mean, if you like to think of it this way, searching a binary search tree involves reducing the data that I have to search through enormously, and the search for a particular item is directed. I'm going to make a decision at each node which path to go along, and supposing the height of the tree was 100, well, it follows that at most 100 simple comparisons need to be made to determine whether a particular mobile number occurs within this um, million or so phone numbers contained in this, what in fact is a database. So what I'm inviting you to see is this. A binary tree is pretty good at making a search for data efficient and quick, because I'm going to home in on the number. If the number exists, if it doesn't exist, I'm going to get an answer like, no, there's no more nodes to visit, therefore the number doesn't exist in the database. Okay, so one thing I'd just like you to get a grip on at the moment is that I've got this sequence, and it started off with 11, I can't quite remember, let's have a look at it. Go back, 11, 7, 8, 11, 7, 8, 11, 7, 8, 11, 7, 8. And what I'd like you to look at is that if I could flatten this tree, imagine squashing this tree downwards so that this node tree occurs here, this node occurs just after the tree, this third node occurs just after the 7, and I think this node is going to appear here, and so on, and so on, and so on. And what you end up with, believe it or not, is a perfectly sorted list of numbers. I mean, I started off with what was actually a random sequence of numbers. If I build a binary search tree and then I flatten it in the way in which I've just described, you get a perfectly sorted sequence of numbers. That's quite interesting. I mean, you can sort a sequence by constructing a sequence of numbers. And I'll remind you guys who were actually on the course last term that we had a quick look at sorting algorithms, for example, bubble sort, and even we had a quick look at quicksort and so on. Different ways of sorting a random sequence of numbers into a sorted sequence. Here's another way of doing everything. So for the guys who weren't present last term, I'm just indicating that this is something that we have covered, and there's some material on the Pharos that will actually guide you a little bit if you're interested in sorting materials. Okay, so we're looking at, well, technically it's algorithms, rules for visiting every single node in a tree without missing any out and doing it systematically. There are 3 principal ways of doing this. So traversing is the process of visiting every node in a well-defined manner, or systematic manner. And there are 3 ways, and these are in order, pre-order, and post-order. And what I'm about to show you might appear to be quite challenging, but hopefully by the end of the session the clouds will lift and you'll see everything in a blindingly clear light. Right, but it's worth putting a bit of effort into what I'm talking about. And the tricky bit, I guess, is the transition to performing a traversal of a tree in Java. And that is one of the reasons I took a preliminary top-level view of Java before presenting you with this material. So please check that material out. And one of the important documents is just a document entitled Objects. So the names above give you an indication of the order in which the root node is traversed with respect to its branches. What on earth am I talking about? I'm first of all going to discuss what's called in-order traversal. And what that means is that the nodes are visited in the order left, root, right. So what on earth am I talking about? It means starting with the root to traverse the tree. In other words, to visit every single one of these nodes. And how many there are? 3, 6, 7, 8, 9. There's 10 altogether. Well, I can visit the first very easily. I'll just go visit the root node. So the rule is I explore the left branch for as far as I can go. I go all the way down. So I find node 7, ignore it, then go down the left branch, and I come to 3, and notice that 3 doesn't have a left child. So what I'm going to do, according to the rule, I visit the root, and I'm going to mark that fact by putting a green dot on this node. This is playing the role of a root, and 3 again doesn't have a right branch. So what in effect I've done so far is that I've explored 7's left branch completely, and I'm visiting this node, which is playing the role of a root, I guess, because it's got a left branch and a right branch. So the rule tells me explore the right branch. So here I go. I come across 8, and processing or outputting the value 8, and I'm marking that fact by putting a green dot here. And 8 doesn't have a left child, it doesn't have a right child. So I've finished exploring the right root. So I've completely explored the left root of the actual root of the tree completely. I've explored this subtree, what I'm putting a ring around now. And the way in which I did it, I go all the way down to the left until I can't go any further down the left, and mark the node with a green dot. I haven't got a right tree to explore, so I've completely explored 7's left child, left subtree. I've done that completely. So the rule says mark this node as visited, and if you want you can output the value 7. Now explore 7's right hand tree. Well, okay, can do that. Here we go. I've just got one node, doesn't have a left or a right subtree, so mark this node for whatever purposes that you're looking at this node. You might want to just output or access this value. So I finished processing the left hand side tree. So I mark the original root node, and then I'm going to start exploring the root node's right hand tree in exactly the same way. It tells me to explore the right child, so let me do that, and I get to this node here, and the rule tells me explore the left branch. Okay, I'm doing that, and I can continue exploring the left branch because I'm repeating the rule. Uh, one doesn't have a left child, it doesn't have a right child. So I'm going to mark this node with a green dot. I've finished exploring one, so it's 15. This should be node containing the value 15. I've explored this left-hand subtree, so I can mark this node. And I'm told by the rule that I've got to explore the right-hand tree. Well, let me do that. Here we go. 20, this node here, 20, doesn't have a left child, doesn't have a right child. So mark it. Mark it. I can't explore its left child. I can't explore the left child or the left branch. So what I'm going to do is to visit or mark or process what in effect is the root of this tree, which is 20, by placing a green dot here. So when I've done that, I've explored 25, this is 25's left hand subtree. And the rule says, well, mark this node and explore the right branch. Well, let me do that. I'm going to explore this. I can't. I come to 2. 2 doesn't have a left branch, so I'm going to mark the node. But it does have a right branch, so I'm going to explore that. I get to 3. 3 has neither left child nor right child, so mark the node and go all the way back home. So the rule for in-order traversal, in effect, is follow the left branch as far as you can, i.e. until a node doesn't have a left branch, then mark the node that doesn't have a left branch and go to the root, visit the root, look at the data in the root or whatever, and then explore the right child by going to the instruction marked with star. So I'm just doing exactly the same again. So please think very carefully about that, and hopefully you won't have any problem with it. So in-order traversal for this tree is that I'm actually going to print out, first of all, this is the first green dot, if you recognise. Print it out, you get 3. Then this is the root that you visited. Sorry, this is the node that you then visited. Print it out, you get 7. And then you explored the right-hand subtree and no left or right branches, and output the value 8. You output 8. Then you go back up to the original root, print the value out, you get, it's actually 11, 1, 1 here. You get 11 here. And then you next visited this node, which is 12. Then you visited this node, which is 15. Then you visited this node, which is 20. And then 25. And then 28. Then 35. So you're getting that out. And this reflects the fact that what I said about a binary search tree or any other tree, if you squash it flat, you're going to get a sorted sequence. 3, 7, 8, 11, 12, 15, 20, 25, 28, 35. So it can be noted that the numbers are obtained in sequence, in the correct order. An in-order traversal of a binary search tree actually gives you elements, sorted elements of the sequence. So move on to pre-order traversal, and the order in which I'm going to investigate this tree, in other words, is first of all you look at the root, then you explore the left branch, then you explore the right branch. If there isn't a left branch, then you just explore the right branch and repeat everything. Repeat. You'll come to a node, then look at its left branch, then explore its right branch and do exactly the same thing. So let's have a look at pre-order traversal. So the rule says, sorry, I've just slipped there. Wait a minute. Wait a minute. What am I doing? Pre-order. Um, what the rule says is you, starting with the root, you visit what in fact is the root. So you're here. You put a green dot at the side of the node. Then you traverse the left-hand branch and apply the rule. Okay, so you mark the node with a green dot and then explore the left-hand tree, and notice that you come to a node which doesn't have a left child, doesn't have a right child. So you simply, you just put the green dot to indicate the fact that you first of all are visiting the node itself. Forget about exploring the left and the right branch. There aren't any. So what you do is to then explore 7's right branch, because it says first of all visit the root 7, which I'm thinking of as a root. It's actually an ordinary node, but as far as the algorithm is concerned, it's behaving as a root. Then explore the left branch. Done that. Now explore the right branch. You come to a single node. Indicate that you visited it, first of all, by placing a green dot by its side. No left child, no right child. So you go all the way up here and explore 11, the original root's right-hand branch in exactly the same way. So you come across a node, mark it, and explore its left branch. Come across a node, mark it, and sorry, I've just keep slipping pages. And then go down the left branch of the tree. You come across a node, mark it, no left child, no right child. So you've dealt with 15. According to the rule, you've got to explore the right-hand branch. Okay, that's easily done. Mark this node with a green dot, no left or right child. So you go all the way up here and start exploring the right-hand branch of node with value 25. You come across a single node, mark it. There's no left-hand branch to explore, but there is a right-hand branch to explore. Explore it. Well, there's a node, mark it. There's no left-hand branch, there's no right-hand branch, so you go all the way back. You're finished. As you can see, just by looking at the presence of all the dots, you've visited every single node in the tree. And if you visit the nodes in a pre-order traversal, you get 11, 7, 3, 8, 25. All right, I'm just reading out the nodes with green dots. 11, 7, 3, 8, 25, 15, 12, 20, 28, 35. All right, and one reason that computer scientists are interested in performing a pre-order traversal is to, after having analysed part of a program or some mathematics and put it into what I guess is like a syntax tree or a grammar tree that you may or may not have studied in school. For example, if you consider this statement, which, let me read it out to you, is add the result of, first of all, multiplying A with B and C. This is called prefix notion. I can actually represent that by means of putting the main operator, which is add, as the root, and on the left branch I'm going to write the operator multiply, which you find here, with its two parameters, two arguments, a and b. So I'm adding whatever this expression gives me to C. So I'm adding all that to C. So the operators are stated before the operands, before the actual parameters that you're passing to the operators. And in prefix notation is used by compilers and calculators, and the tree of this operation is given. So I'll just leave you to think a little bit about that. And I mean, usually we write the equivalent expression in infix notation. I place the operators between the operands. So the sign for multiplication occurs between A and B, and C operates on this value and this value. So it's infix. So we're now looking at post-order traversal, and the rule for systematically visiting every node in a tree using this algorithm can be represented by: you explore the left tree, then you explore the right tree, then you visit the root, you process the root, you process the node, if you like. So I'm starting at the root. What it tells me to do is to explore the left tree, which I'm going to do. I'm just exploring it, and as far as I can. Well, 3 doesn't have a left root, so start exploring the right root of this node. Well, there's nothing there, there's no right node, and it tells you to mark the node. So I'm putting a green dot by the side of this node. So I've explored the whole of 7's left-hand branch, and what the rule says, now explore the right-hand branch. So I'm going to do that by exploring the left-hand, exploring this this connection, and I come to this node 8. Doesn't have a left or a right branch, so I can't explore the left branch, can't explore a right branch. But what I can do is to mark the node as having been visited, or having been accessed, or outputting the value here. So as far as 7's concerned, I've explored the left-hand branch, I've explored 7's right-hand branch, this thing here. And then I've got to mark the node. Look, it says mark the node, or the root. Mark it. So at that point, I've explored it's 11, node 11's left-hand subtree. And it tells me to now explore 11's right-hand subtree. So let me do that. Let me do it. Look, here we go. I'm going to explore, first of all, the left. I find a node, I'm going to explore its left-hand branch, and there's no stopping. At this point, there's no left-hand branch, so I stop. There's no right-hand branch either. It says, look at the right-hand branch, there's no right-hand branch. So what I do is to simply indicate that I've got a node which I've accessed or processed in whatever way. And at that point in time, I've explored 15's left-hand branch. Now let me explore 15's right-hand branch. There we go. I find a node, no left, no right-hand branch. So what the rule says, mark the node. Here it is. So I'm putting a green dot against the side of this node here. So I've processed 15's left-hand branch and its right-hand branch. What the rule says is put a dot to indicate that you're looking at 15th value. So at this point in time, I've fully explored 25's left-hand branch, as I had to do. Now explore its right-hand branch. Okay, here I go. I find a node. There's no left-hand branch, so I explore its right-hand branch. I come across 35. 35 doesn't have a left-hand branch, doesn't have a right-hand branch. So the rule says mark this node with a green dot. And I've now finished I've finished exploring 28's left-hand branch and 28's right-hand branch. So I mark the fact that I'm visiting this node, or processing this node, or outputting the value of this node by a green dot, and at that point in time I've fully explored 25's right hand branch. So what I do is to put a green dot against the side of node 25, and so I've finished exploring 11's left hand branch and 11's right hand branch. So all that remains to be done is to put a green dot on the side of this root node, and I'm finished. So I'm afraid I can't quite actually, I'll change this before I release this document to you. I've overwritten some of the text here. So post-order traversal, if you've understood this, all I have to do is to find the first node that I visited, which is 3, and print it out. I've got a 3 here. Then the second node I visited, which is this node here that contains 8, print out the value 8. This is the third node I'm actually inspecting or visiting, so print it out 7, and so on. And eventually, following all the green dots, I actually output the contents of the original root node, which is 11, because I've got a 1, 1. The two characters 1, 1 don't fit into this circle, so I get 11 here. Okay, so in computer science, sometimes you find an arithmetic operation in the form of you're multiplying A with B, and then you're adding the result of multiplying A with B to C, and you write the expression that. And the way in which you write, I mean, it's quite unintuitive. The way in which you write out this operation is it's in reverse Polish notation, simply because there was the Polish logicians quite a long time ago used to develop all their compiler theories in this way, and it's quite convenient to use expressions of this form in compiling in order to evaluate expressions. So for example, again, is this right? Yeah, what this tree tells me is that what I need to think about is to add this expression with that expression. And if you do a post-order traversal of this tree, you will actually get AB, mult, C, and finally add. You'll be able to recreate the expression in this order. Don't worry too much about that, because what I want you to worry about is implementing binary search trees. So in binary search trees, for each node, data about the left pointer and the right pointer and value of the elements are stored. And cells, or actually what I might call nodes, which is a way of thinking about a little data structure, can be used to implement this. And you could actually implement binary search trees using arrays of records, where each record stores data about the left pointer and the right pointer and the value of the element. And what do I mean by that? I'm thinking of trying to represent a node by, let me go back to a numerical example. I'm thinking about trying to represent this node, which contains a value 25 and represents the fact that there's an element within the node that points to or refers to another node, and might call it a left pointer. It points to the next node. I mean, of course, the left node might be a null pointer. There might not actually exist. If 25 doesn't have a child, or no children at all, both left and right references are going to be null. They're null. There's no actual node being pointed to. And let's just explore that idea a little bit. And let me see. So what I intend to do, and this follows on from our earlier discussion of Java, a little bit anyway. So I'm going to use a class, a Java class, to represent each node instance. And here is the class. So I've got a curly bracket, end curly bracket, and what's contained here is an integer value called value, and a variable called left, which is of type node, and another variable called right, which is of type node. So value is of type integer, left is of type node, right is of type node 2. And I've got a little routine here which is going to help me initialize this integer variable when I create an instance of this class. Here's the class, and what I can then do after I've defined node is to create as many nodes as I want to, simply by creating an object from this class. It'll be a node object from this class. And I can easily do that simply by writing, like, Chris Kinberg is a new node. And Chris Kinberg will be the name of an actual node. And when I create the node, I can actually supply node with a value like 155, and 155 is going to be assigned to this integer variable. And the way in which I do that is to use this, which is behaving as an operation or a procedure. And in fact, it's neither. It's called a constructor, and the constructor is going to be executed at the moment you use new. In other words, at the moment you create an instance of this class. So the other thing I want you to know is that the class that I've just defined, the class node, is actually being defined in terms of itself, because node contains two variables of type node. But that's perfectly okay. There's no problem. Just go along with this for the time being. So it's a recursive definition. Node, the class node is itself defined in terms of node. Okay, so just bear that in mind, but don't be too worried about that. The idea is, what I can do is to give a name to the node object I'm creating in Java by writing this expression. And I'm going to supply a value. Like this value could be proxy for the number 25, the integer 25. What the result of executing this line of Java will be, as discussed in my earlier talk on objects, is I'm given an object and I'm calling it node 0, and it looks like this. And it's got two variables, left and right. And if I wanted to, I can assign this second node, which has a value 2, and I created it, I'm calling it node 1. It's a new node which has a value 2. So the value 2 is assigned to the integer variable in the object, and it too has a left reference to a left branch and a right branch. So if I have a look at this node, to produce this tree consisting of a root node, i.e. node 0, and a leaf node, node 1, I can assign node 1 to node 0's right variable. In other words, what I do is to write the name of the node, which is node 0, dot right, so I'm accessing the variable right, and I'm assigning to it the value of node 1. Node 1 is actually a node. It's this object here. So at the moment, of course, node 0 doesn't have a left branch. So what I should really do is to, let me have a look at this. I've actually, by default, assigned right and left to be the null nodes. I mean, it's a bit like, a 0. There's nothing there. There's nothing there. And so I've made a mistake here. It's in the table below. Okay, we're going to have a little exploration of a table in a moment. So node 0 doesn't have a left branch. The value of the left is null, and the left child of node 1 is also null. And that's okay. And I guess that the right node is also null by default. I mean, all I've done is to create one node, given it a value to store, and created a second node, which looks like this, and I've given it a value 2, and I haven't done very much else, but I've got a tree of 2 nodes. It's miraculous. Okay, so have a look at this. This is setting things out a little bit in unnecessary detail. My node 0 is going to be this node, and I'm going to assign the value 11 to it. So the data it contains is the integer 11, and using this, if I replace value 1 with 11, I actually get that, and this would be 11, and this would be null, and this will be null. So I've got the root node, built the root node. Have a look at the second row. Well, I need to create a new node by writing new node 7. So I'm creating a new node with the value of 7, and the left. Okay, so going back to the first row, node 0, this is node 0, node 0's left pointer is going to point to node 1. It's going to point 1. And all I have to do is to write the word right dot left equals node 1. So at that point in time I've got the root node, which I started with, it contains the value of 11, and a second node, it's node 0's left child, which contains the value 7, and I can go on. In Java I can easily build this tree. This table is a bit of a distraction, I reckon, but contains all the detail. So the first row of the table represents information about node 0. It contains 11 as data, and the left branch of the tree is given by reference to node 1 and contains the data 7. And node 0 refers to a, sorry, this is terrible, sub-branch it should be, horrible late night typographical error, which begins with node 4. Node 2 contains data 7, and it has a left and a right branch which begin with node 2 and node 3. So you can probably work out all the fine details. And what I can now do, if I can build this tree, I can specify Inordinate Traversal in Java, and I've got a little operation called inorder. I'm defining an operation, and it takes a node, some node n, as an argument, as an operand. And can anyone tell me what inorder? Let's check out what inorder does. Let's check it out. Let's go way back. Find out what inorder does. There's post order, post order, post order, pre-order, 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 in order. Alright, it's explore the left branch, visit the root, and then explore the right branch. So so where were we? We're about here. Alright. So have a look at this. If you like, think of it in terms of an operation by means of a sequence of instructions. Right, and this is almost pure Java. So n, you will recall, is an object, and n you can access anything in n by prefixing it with the object name n. So what I want to do is to ask the question, if the left subtree is not equal to null, then apply the in-order algorithm to the left branch. And when you've done that, you print out the data in the node n. And when you've done that, okay, so I didn't have to go back, it was already here. Left, root, right. So what I'm doing is to explore the left branch. How do I do that? Well, I'm just going to run this routine on the left branch, and I get the f branch by looking at n.left. That's going to return a root. Sorry, it's going to return a node, and I'm going to repeatedly explore the left branch as far as I can. If I come across a node that doesn't have a left branch, I stop and I print the data in the node out. And when I've done that, providing there is a right branch to explore, I'm going to explore the right branch. How do I do that? Well, I'm applying in order the procedure in order, the set of instructions again to the node's right hand branch belonging to node n. And why have I got that? So I don't need this line here, so that's why I've just commented it out. Okay, so if you think about it, what we're doing in Java here, and don't worry about it because we're going to think about this and learn how to use all these operations. If you think about it, what I'm saying is, in order do an in order exploration of the left subtree, then mark the node or the root from wherever you start, and then when you've done that, explore the right hand node. So what I'm doing here, I'm exploring the left hand subtree rather. I'm visiting the node by printing its data out, printing the node or the root's data out. How do I do that? Well, n is the node that I'm looking at, so n dot data, output that, print it out. And providing there is a right hand branch, explore the right hand branch. Okay, so this traversal's efficient in searching an element from the tree. And I could do exactly, and I'm not going to spend much more time on telling you about the three different ways of traversing a tree, but this is, apart from this capital V, which shouldn't be here, it should be lowercase, this is almost pure Java. And what pre-order traversal can be described as, first of all, visit the root or visit the node that you're looking at, then explore the left subtree, then explore the right subtree. This is exactly what I'm doing here. You print the data in the node n. I mean, it could be an arbitrary node, or it could be the root. If the left hand subtree is not null, then pre-order, explore using pre-order the left subtree. And then, when you finish doing that, if you, providing that the right hand subtree is not null, then explore using pre-order the right hand subtree. And exactly as similarly, in similar fashion, you can implement post-order traversal, which means explore the left subtree, then the right subtree, and finally visit the root or the node that you're looking at. Can be written in this way. Lowercase v, of course. To do a post-order exploration of a particular node, if the left-hand branch exists, post-order it. If the right-hand subtree is not null, in other words it exists, then explore it using the post-order algorithm. And finally, you access the node n itself by just printing out the data field found within this node object. Okay, I've given you a summary of everything I've spoken about, but I guess I should really check through. Tree's non-linear, it's two-dimensional, it's cycle-free, three ways of traversing a tree. I've told you what a binary tree is, and I've shown you how to construct a binary tree. And with a bit more difficulty, especially for those who have only just joined the course, I'm showing you how to implement a binary search tree for a given sequence of numbers. And it does have a couple of nice properties, namely, if you do an in-order traversal of a binary search tree, you're actually effectively sorting the data that you put into the tree. You've sorted it. You're seeing what the sorting of the sequence results in. Here's the rule for constructing a binary search tree. And to implement the traversal algorithms, we're using a recursively defined procedure in every case. And as I've said before, I mean, just having a look at this post order, I'm defining a post order operation, but I'm using post order. I'm using the same set of rules to explore simpler parts of the tree. It's the left subtree and the right hand subtree. So I'm entitled to define post order, the operation, in terms of itself. And you're going to have to think a little bit about that. A simple case that I suggested you think about was to try and define your ancestors, and you'll find that you'll probably have to end up defining the idea of having an ancestor recursively, in the sense that, well, okay, first of all, your mother and father technically are your ancestors, but any ancestor of your parents are also going to be your ancestors. Okay, so you can't give an explicit definition of what an ancestor is without defining it in terms of itself. Activities, what I'd like you to do at some point is to create a binary tree consisting of strings: Google, Dropbox, Facebook, Twitter, Instagram, Amazon, Zoom, Skype and WhatsApp, and construct a binary tree if the first element is the root node and the following elements are entered in the order given. So I want you to construct a binary search tree consisting of these strings. And slightly more tougher, list the order of nodes in which they would be visited if you're using in-order, pre-order, post-order traversal. And we'll skip that for the moment. So end of topic questions. And I'll finish there, but I'm going to create a very short follow-on video clip to demonstrate the running of the Java